Let's take a look at an example where we might have to worry about different densities of fluid. A common one that we have to deal with in the environmental industry is when we have a fuel spill. So maybe a leaking tank spills some fuel into the ground, percolates down through the Vadose zone, and then stops at the water table because it's lighter than water and just ponds up on that water. So if we then put a piezometer down through there, we drill a boring down through that lens of fuel sitting on top of the water, we end up with something that looks like this. We have this piezometer here, we have a column of water, and above that column of water is a thin layer of fuel. So we can use a little interface measuring device to find the depth to the top of the fuel, and that's 12.2 meters in this case. And then the bottom of the fuel is 13.1 meters, and then the bottom of the well is 22.8. So what we want to know in this particular case is, what is the pressure at the bottom of this well? What is the pressure at the bottom of this well? So how do we solve this? So we're given everything that we need here. All we need to know now is our relationship between fluid depth and pressure. And we know that is the hydrostatic equation, but sometimes I like to start with just the definition ahead if I forget. So we know that H is P over gamma plus Z, right? That's always true when we don't have any velocity. Okay, so this is the static head. And so we know that then the change in head is equal to the change in pressure divided by the specific weight of the fluid times the change in the elevation or depth, depending on what your reference frame is. So we know that in a static fluid, in the same fluid, head will not change. So if we look at what's going on with the pressure in each one of these fluids individually, then we can simply solve for the change in pressure is equal to minus gamma times the change in elevation, which is equal to gamma times the change in depth, right? So what have I done here? I've just assumed that the datum is, we're working with elevation above some datum, and I've just changed this to be with depth. All right. So this is what we know as the hydrostatic equation. And remember that this is only true in each fluid, so we have to do this one fluid at a time. So let's try and solve this to find the pressure. So I'm going to have got each of my interfaces numbered here. So I'm going to start where I know the pressure, and I'm going to work my way to where I don't know the pressure. I'm going to start where I know the pressure, work my way to where I don't. And this is always a useful approach whenever you're dealing with fluid mechanics. So where do we know the pressure in this problem? Well, we know the atmospheric pressure is right here, right? We know this is an open surface, and so that's atmospheric pressure. So I'm going to start at point 1. So the pressure at point 1 I know is 0 gauge. All right? So I don't have to do any work to do that. The pressure at point 2 is going to be the pressure at 1 plus this change. So it's going to be plus gamma of the fuel times the change in depth. Right? So I've gone from point 1 to point 2. And then to go from point 2 to point 3, I'm going to start where I now know the pressure at point 2. So the pressure at point 3 is the pressure at point 2 plus gamma times the change, or gamma of the water times the change in depth. And I can write from 2 to 3, and this one is from 1 to 2, right? So that means the pressure, if I substitute this, the pressure at 3 is equal to the pressure at 2, which is also this. So I can substitute in P1 plus gamma fuel, change in depth from 1 to 2, plus the second term, gamma of the water times the change in depth from 2 to 3. All right? So when it's all together, you can kind of see you start at the pressure where we know is actually 0, and we increase the pressure at the rate of the specific weight of the fluid, and then we increase the pressure at the specific weight of the water. And then all we have to do now is plug in those values. So the pressure at 3 is equal to the gamma of the fuel, which is 6670 newtons per cubic meter. And we multiply that times this change in depth. And so that's 13.1 minus 12.2 meters. And then we add, I'll write it down here, then we add the gamma for water, 9810 newtons per cubic meter. And we multiply times this other change in depth, which is 22.8 minus 13.1 meter. And that comes out to be a pressure at the bottom there of 160 newtons per square meter, which we know is a Pascal. Right? So that would be about 101.2 kilopascal, which is approximately equal to 1 atmosphere. And the significance of that 1 atmosphere is not much, it's just coincidental that we're at that pressure. So here is our pressure at the bottom of that water column with the fuel sitting on top.